Ah, the parabola. You've become pretty familiar with these graphs recently. We can tell all kinds of things about a quadratic function from its graph. But today we're going to take a look at how to create a parabola from its standard form equation. Let's get into it. Ultimately, when we graph quadratic functions, we'll use a solid parabola like this one to represent the infinitely many individual points on the function. But how many individual points do you think you need to be able to accurately graph the full U shape of the parabola? 10 points? 8 points? Fewer than that? Does it matter where on the parabola those points are? In your guided notes, plot out how many and which points you think you would need to accurately recreate this parabola. Pause the video here and come back when you're finished. Let me walk you through my thought process. I feel like there are multiple parts of this parabola that I'm going to need to make sure I cover. There's the left side of the U and the right side. I definitely need at least 1 point from each side to know how wide the parabola is, but are 2 points enough? Whoa, definitely not. This looks more like a line than a parabola at this point. Plus, even knowing it's supposed to be a parabola, I still can't tell whether it opens up or down. Taking another look, I think I'm missing a third important part of this parabola. There are two sides, but also the vertex where they meet. The vertex not only shows me that the parabola opens upward, but also how far down the U shape goes. Now I'm up to 3 points. The vertex and 1 point on each side of it. Is this enough to accurately graph a parabola? Let's check. Maybe? Here's how I draw a parabola between these 3 points. Let's overlay the original parabola on top to see how accurate mine is. Okay, I did okay, but my parabola is noticeably narrower at the bottom, which is why all that orange is showing. I think this would do in a pinch, but more than 3 points would be better. I'm going to give this one more try, this time with an additional point on each side, bringing us to 5 total. Yeah, the shape is much clearer with those additional points. I feel a lot more confident about my graph this time around. Let's recap. We've seen that to accurately graph a parabola, we need the vertex and 2 points on each side. One major obstacle still remains, though. When you look at a function like y equals x squared plus 6x minus 7, how do you know where its vertex is? Well, you don't, but we can find it. Remember, parabolas are symmetrical, and the vertex lies right on the axis of symmetry. All we need is 2 points with the same y value, and we can find the axis of symmetry directly in between them. Luckily for us, since I have the equation of this function, I can just substitute any y value and solve to find the corresponding x values. In the first half of this unit, we did a lot of solving when quadratic equations were equal to 0. This is perfect. I could substitute 0 for y and solve to get x values. What will these x values represent on the graph since y is 0? Yeah, they'll be the x-intercepts. Since you're a pro at solving quadratic equations, go ahead and pause the video here and solve this for the x values. I factored and used the zero product property to solve. But you could have solved using the quadratic formula or by completing the square too. And any of those methods should still have given that x is 1 or -7. Since these came from using a y value of 0, these solutions mean the points 1, 0 and -7, 0 are on my parabola. I'll start fresh and plot these 2 points now. My vertex and the axis of symmetry have to be in the center of these 2 points. What's directly in the middle of 1 and -7? Their midpoint is at x equals -3. You may have counted on your graph to find that, or you could have taken their average to get that same result. If my axis of symmetry is on x equals -3, how can I find where, specifically, the vertex is on x equals -3? If I want a point on this parabola with an x value of -3, then I could just put -3 in for x in the equation and find the y value, which in this case is -16. This means the point -3, -16 is on our parabola and, in fact, is the vertex, since it's the point that is on the axis of symmetry. Finally, with the vertex and 1 point on each side like this, we can see the general shape of the parabola. But having an additional point on each side will help ensure we haven't made any mistakes and that our sketch isn't too narrow or too wide, like what happened earlier when I tried to sketch a parabola with only 3 points. We could pick any other x value to substitute and find an additional point, but choosing an x value that's relatively close to the vertex will help ensure it fits on our graph. If I substitute 0 for x, I get that the y-intercept is 0, -7. Once I plot this point, I can use my axis of symmetry to find its reflection. Since this point is 3 spots to the right of the axis of symmetry, we can plot another point with the same y value 3 spots to the left of the axis of symmetry. With 5 total points, the vertex, and 2 points on each side, we can draw in our parabola and feel confident that it's accurate. The axis of symmetry is just a reference, not part of the actual parabola, so I'll remove that from my final graph too. Now that we have a better understanding of what we need to graph a parabola, let's try 2 example problems. This problem says to graph y equals 4x squared minus 16x plus 7. We saw earlier that you'll need the vertex and ideally 4 other points to plot this graph accurately. With that in mind, pause the video here and try this problem on your own first. To find my vertex, I started by substituting 0 for y and solving to get the x coordinates. I solved using the quadratic formula this time to get that when y is 0, x is 3.5 or 0.5, giving us these 2 points, which I'll go ahead and plot. The axis of symmetry has to be halfway between these 2 points. By counting or finding the average of the x coordinates, I could tell that the axis of symmetry is going to be between them at x equals 2. If you got stuck before you were able to find the axis of symmetry, this is a great opportunity to pause and try to finish off the problem on your own from here. I know the vertex will have the same x value as the axis of symmetry. If we substitute 2 into the equation for x, what do we get for the y value? Substituting 2 for x gives us a y value of -9. So I'll plot 2, -9. My parabola is taking shape, but I want one more pair of points to make sure my graph is accurate. I don't want to deal with numbers that are too big, so I won't go too far away from the vertex. I'll use an x value of 0, which gives a y value of 7, making the point 0, 7. Since this is 2 spots to the left of my axis of symmetry, I can plot a mirror image point 2 spots to the right of the axis of symmetry. And now, with 5 total points, I feel confident drawing in my final parabola and removing the axis of symmetry from my graph. This second example problem says to graph f of x equals x squared minus 2x plus 1. This is written in function notation with f of x. But remember, this is just another way of saying y equals. Pause the video and try this problem on your own now. I started by substituting 0 for f of x, hoping to find the x-intercepts of this function. But when I factored to solve, check it out. The factors are the same, so there's only one x-intercept, 1, 0. I can plot this, but I definitely can't find the halfway mark between the x-intercepts if there's only one x-intercept. So now how do I find the vertex? Well, if a parabola only has one x-intercept, then it can't go through the x-axis, because then it'd have to go back through the axis again like this, or this, to create that U shape of the parabola, which would make a second x-intercept. In fact, if a parabola has one x-intercept, then that x-intercept is the vertex. If you're tempted, you can pause the video here and see if you can find a way to draw a parabola with one x-intercept without that x-intercept being the vertex. Go on, I'll wait. Okay, so 1, 0 is the x-intercept and the vertex of this parabola, which also means that the axis of symmetry is x equals 1. Now I just need to find 2 points on either side of the vertex. If you were stuck before, pause the video again here and try to finish this off on your own now that you know that 1, 0 is the vertex. It doesn't really matter which x values you substitute to find some additional points here. The only thing to consider is that our graphs have limited space, so staying near the vertex should help ensure that your y values don't get too large. I'll go one space to the left and substitute an x value of 0, which gives a y value of 1, so I'll plot the point 0, 1. And then I'll go one more space to the left and substitute an x value of -1, which gives a y value of 4. So I'll plot -1, 4. I can use the axis of symmetry to reflect both of these points and find the opposite side of the parabola. Now with my 5 points, I can feel really confident in plotting a nice rounded parabola through them. Perfection. Wow. So when it comes to graphing parabolas, the vertex is really the key. Luckily, substituting 0 for y and solving for the x-intercept, or x-intercepts, can help. For quadratics with 2 x-intercepts, we know that the x value of the vertex will be in the middle of them. And for quadratics with only 1 x-intercept, we know that the vertex is the x-intercept. If you want to learn what to do for quadratics with no x-intercepts, then you'll have to check out the bonus activities in your PDF. Be sure to complete your guided notes and the online practice first, though. Good luck with that, and I'll see you next time.